This video is just a video of me solving problems from the quiz over visualizing functions of several variables. This quiz covers two standards. The first standard is F12, visualizing functions of several variables, and then I'll handle limits and continuity in a different video. So we're given this function, and we're asked to sketch a contour map of the function in the domain space. So that's in the xy plane. The contour map should consist of 3 or more level curves. And you want to clearly label the values of z used in your contour map. So the first thing we need to do is we need to identify the range of this function. Now y squared minus x squared is just a real number. So this range is going to be the range of the square root function, the square root of a real number. Well, the square root of some real number is always going to be greater than or equal to 0. So I identify that. So the z values, if this is z equals f of x, y, the z values are some number between 0 and infinity. And that's important because I need to choose values in the range for my contour map. Now, our textbook and a lot of textbooks tend to use like constant. They say f of x, y equals c for various values of c. I just prefer to call it z because it just reminds me exactly what it is. So I would set z equal to 0 and see what that level curve looks like. And then set z equal to 1 and z equal to 2, and then we'll see how those level curves change. But the key is to find out what the range is first and then choose values of z in your range. So let's say we have z equals 0. Then we have 0 equals the square root of y squared minus x squared. And then if we square both sides, of course, the square root disappears and we end up with this. And then if we add x squared to both sides, we get this. So if I solve for y, I'll have y equals plus or minus the square root of x squared. So we're going to get plus or minus x there. Y equals x, y squared equals x squared, and if y equals negative x, y squared equals x squared. So this level curve actually consists of two lines, y equals x and y equals negative x. There's y equals x. And y equals negative x on this other axis. Now on both of those lines, z is equal to 0. So we want to imagine that we're slicing our surface at z equals 0. This is what it's going to look like. That's what the slice is in the xy plane. It's just those two curves. Okay, and let's set z equal to 1 and see what that looks like. Then we have 1 equals the positive square root of y squared minus x squared. Again, we square both sides to get rid of that radical. And now we've got 1 equals y squared minus x squared. Well, that's a hyperbola centered at 0, 0. The numbers under the y squared and x squared are just 1. So we go out plus and minus 1 unit in the y direction and the x direction from 0, 0. And we draw a little box. It would look like that. And then we draw lines through the diagonals of that box. Those are the asymptotes of our hyperbola. They actually are already there for z equals 0. And when x equals 0, we see y is equal to plus or minus 1. So our level curves pass through x equals 0, y equals plus or minus 1, and then they approach these curves. Now the rest of these points are just estimates. I'm not actually sure what that looks like. And that's 1 unit up. So on this line, or in this curve and this curve, z is equal to 1. So if you want, you could imagine that coming 1 unit out of the page. In the xy plane, we see these two lines, and 1 unit out of the page, we'd see this. And then as you can imagine, z equals 2 is just another hyperbola. So we're gonna have a bunch of hyperbolas. Square both sides. And now I've got 4 equals y squared minus x squared. Now the standard form for a hyperbola has a 1 on one side, so we'll divide everything by 4. And if you want, you can write that 4 as a 2 squared. So this is a hyperbola centered at the origin. Excuse me. And since we've got a 2 and a 2 under the x squared and the y squared, we're going to go plus and minus 2 units in the x and y direction from that center of 0, 0. And then we draw in diagonals through that box, which already happen to exist, the z equals 0 line. And then when x is 0, on this curve, if x is 0, we see that y has to be plus or minus 2 in order to make that work. So our level curves look like this. Has 2 branches. They open upward like that. And this curve and this curve, z is equal to 2. So you might want to imagine that these curves are 2 units up. 2 units coming out of the xy plane, which you can think of as my piece of paper as the xy plane. Okay. It says the contour map should consist of 3 or more level curves. Label the values of z used in your map. We did. Okay, we're done. Now let's try to imagine what this would be in 3D. It looks like this. And then up 1 unit, we see that as our slice, if we slice it with the plane z equals 1. And then up 2 units, we see that as our slice. You thinking what I'm thinking? Thinking this is a cone? Looks like a cone. Looks like a cone that opens on the y-axis to me. Let's see if that's the case. It says use the level curves that you just drew and your knowledge of quadric surfaces to graph the function in R3. So what I do is I set z equal to f of xy. And I don't write f of xy, I just write the function down. And then I take this equation and I rearrange it and try to make it look like the equations of our quadric surfaces. So first of all, I notice that z is greater than or equal to 0 because it is a positive square root. Then keeping that in mind, I square both sides. And we have this. And then we might subtract z from both sides or add x squared and subtract y squared from both sides. I think I'll do that. So I have x squared minus y squared plus z squared equals 0. And remember, z is greater than or equal to 0. Now, I hope you recognize this. All 3 variables are squared. 2 terms are positive, 1 term is negative, and the right-hand side is 0. This is the equation of an elliptic cone. It's actually a circular cone. The center is 0, 0, 0 because we're not subtracting anything from the x, the y, or the z. And it has symmetry along the y-axis. So it opens in the y direction. And that's consistent with our picture over here. See that when z equals 0, we see this, and then 1 unit up, we see that, and then 1 unit up, we'd see that. We're taking these slices that are parallel to the xy plane. And I think those curves are just going to get larger and larger. That's exactly what we would see if we had a cone opening on the y-axis. I hope you can add that third dimension in your mind and imagine what that looks like. Okay, so now I'm going to try to draw the top half of an elliptic cone centered at 0, 0, 0 that opens in the y direction. When in doubt, just draw me the best picture that you can, and then put a big arrow and say, that's a cone. That's the top half of a cone. That's fine. It doesn't have to be perfect. I love art. I'm not an artist. My dad is an artist and my sister is an artist. They are very good at things like this. I am less good at them. I don't expect everybody to be artists, but we try. We do the best we can. Maybe it looks like that, approximately. And you have to imagine that there's some other side of the cone that we can't see. So this is the top half only of an elliptic cone centered at 0, 0, 0 that opens in the y direction. And you can imagine if we keep slicing it, we're going to see something that looks like that. It's a very good sign. Okay, so the next question says, find the domain of a function. Or no, wait, it doesn't say that. It says, the domain of a function of two variables is a region in the xy plane. Describe the algebraic process used to find that region. This is the same algebraic process you've been using to find domains since pre-calculus. It's pretty simple. Domain is a set of x values, or the set of input values that will give you output values that actually make sense in the real number system. That's the implied domain. In this class, if you are given a function that's given by an equation, its component parts are functions that you've already studied. So polynomials, rational functions, trig functions, inverse trig functions, root functions, all those exponential functions, logarithmic functions, all those functions you're familiar with. The domain is going to be the set of all xy pairs for a function of two variables for which you're not doing any of those things that cause problems when you're trying to get a real number. So this is how I would answer this. It says, describe the process used to find that region. Let's say the domain of f of xy is the set of all xy that do not cause these three problems. Anything else will work. Division by 0. Can't take something and divide it into 0 pieces. It doesn't make any sense. We also cannot take even roots of negative numbers. And we can, but not in this class. These are functions of real variables that have real outputs. Even roots of negative numbers, like the square root of -4, that's a complex number. And those are very nice numbers, but we're not interested in them in this class. So the domain is a set of all xy that do not cause division by 0, even roots of negative numbers, or logarithms of negative numbers, or 0. Turns out you actually can take the log of a negative number, but not in this class. Again, it's going to be a complex number. Okay, so describe the algebraic process used to find this region. So we'll say exclude any xy in R2 that cause the problems above. Then the domain is all remaining xy pairs in R2. Just like pre-calculus. You want to exclude the values that cause problems, and then everything else is fine. So that's how we find the domain. Okay, next question. It says you've got a function of 3 variables. It says find the domain of this function, explain your reasoning. Well, this is a function of 3 variables, so the domain is a subset of 3-dimensional space, and we've got a radical. Now the rules are the same with functions of 3 variables. You just aren't excluding x, y's that cause problems. Here you're excluding any x, y's, and z's, any x, y, z ordered triples that cause problems. So the domain of F is going to be the set of all x, y, z in 3-dimensional space such that, well, I can't divide by 0, there's no division, so I don't have to worry about that. I can't take the logarithm of a negative number or 0, there are no logs, so I don't have to worry about that. But I do have a radical. I cannot take the square root or any even root of a negative number. That's not allowed, not in this number system, not in the reals. So the domain of F is the set of all ordered triples such that this is non-negative. So the expression under the radical must be greater than or equal to 0. And actually, I've got a perfect square plus a perfect square plus a perfect square. So that's going to be greater than or equal to 0 all the time. This is a non-negative number. That's a non-negative number, and so is that. So the domain of F is all x, y, z that satisfy this. Well, all x, y, z do satisfy this. So that's all of R3. And I'll say because that expression under the radical is greater than or equal to 0 for all x, y, z in R3. Next question says, find the range of this function, explain your reasoning. Well, again, with range, you're just looking for the outermost function. Now this is not something that's always easy to handle, but there are some cases that where we can look at the function and find the range pretty easily. This is one of those cases. We know that square roots always give us numbers that are greater than or equal to 0. So this by itself would have a range of 0 to infinity, but then I multiply it by -1. So I took this number that was positive or possibly 0, and I multiplied it by -1. Now it's negative or possibly 0. So the range of F, it's the same as the range of the negative square root function. In the reals. And the range of the negative square root function is -∞ to 0. So I said this, how do I explain that? Well, I guess I could say because square root of x is always greater than or equal to 0, which implies square root of negative square root of x is always less than or equal to 0. It's equivalent to saying that. Okay, so our range is all negative numbers are 0. The domain is any x, y, z in R3. Now we're asked to sketch several level surfaces of the function. It says, be sure to clearly label the values of w that we're using here. So on the last problem, we were sketching level curves. We set z equal to a constant, and then we saw what those curves looked like. Now we're trying to visualize a function of 3 variables, which is difficult to do because we live in 3-dimensional space. So what we do instead is we sketch level surfaces. So we choose values of w in the range, which is why it's really important that we find the range first. And then we sketch the resulting surfaces. The question says sketch several level surfaces. I usually do at least 3. So our range is -infinity to 0. So let's look at w equals 0. So I've got a negative square root of x squared plus 4y squared plus 16z squared equals 0. Now square both sides. If you want, you can multiply both sides by -1 first. It doesn't matter. We're going to square it anyway. A negative times a negative is a positive, and then we end up with x squared plus 4y squared plus 16z squared equals 0. Now the only way that happens is if x, y, and z are all 0. Otherwise, these would be positive and we wouldn't get 0 over here. So this level surface is pretty boring. It's just a single point. Okay. Now let's look at w equals 1, so, or -1. 1's not in the range. I'd have a really hard time getting a 1 out of this. So let's let w equal -1. So we have -1 equals negative square root of x squared plus y squared plus 16z squared. And I forgot my 4. There we go. Multiply both sides by -1 and then square both sides. And we'll have 1 equals x squared plus 4y squared plus 16z squared. Now, this is an ellipsoid, excuse me, and it's centered at the origin, but it's not quite in the right form. We need an a squared, b squared, and c squared under the x, y, and z. And I'm multiplying by 4 and I'm multiplying by 16. I'd really like to be dividing by something and dividing by something here as well. Well, we can do that as long as we remember that multiplying by 4 is the same as dividing by 1/4. Because remember, if you divide by a fraction, you multiply by the reciprocal. So this is really the same as that. And multiplying by 16 is the same as dividing by 1/16. Now, to write this in standard form, normally we like to have an a squared in the denominator, a b squared in the denominator, and a c squared in the denominator. So I'm going to take each of those numbers and write them as perfect squares. Now, I can see from this that I've got an ellipsoid centered at the origin. Oops, 0, 0, 0. I'm gonna get out the whiteout, guys. And have this pretty quiz key on our course website. There we go. And then we're going to go plus and minus 1 unit in the x direction, plus and minus 1/2 of a unit in the y direction, and plus and minus 1/4 of a unit in the z direction. Well, there are no tick marks on my axes yet. Yes, the important part is that we're going like 4 times as far in the x direction as we are in the z direction, and half as far in the y direction as we are in the x direction. So I'll just make that 1. Actually, I think I want to extend that out further because we're going to do one more level surface, aren't we? I'll let that dry for a second. But I want to go half as far in the y direction. And then just 1/4 of a unit, 1/4 of that distance in the z direction. Okay. So I've got an ellipsoid that looks like this in the XY plane. It goes up to this. Oops, it's a little bit hard to see, sorry. Okay, it's not great. That's when you just draw an arrow and say ellipsoid. That's fine, it's good enough. Okay, so we've got W equals -1, then we get this. So it's W equals 0 right here. And then this is W equals -1. So if W is increasing, I would go from -1 to 0, and then I would stop. Okay, well, let's see what we get when W equals -2. I think we already know the answer. It's going to be another ellipsoid. Question is, which one? Well, I have 4 equals x squared plus 4y squared plus 16z squared. And then we take that and we divide both sides by 4. And I'm going to write that 4 as a 2 squared. So I've got x squared over 4, which is 2 squared, plus 4y squared over 4, which is just y squared, over 1 squared. And then I'll have 16z squared over 4, which is 4z squared. But multiplying by 4 is the same as dividing by 1/4. And dividing by 1/4 is the same as dividing by 1/2 squared. Okay, so we see we have basically the same shape. It's just going to be longer, just expanded even further. We're going to go out plus and minus 2 units in the x direction, plus and minus 1 unit in the y direction, and plus and minus 1/2 of a unit in the z direction, which is why I use the white out right there so I can keep drawing. If that's 1, well, then that must be 2. That must be -2. And again, it doesn't have to be perfect. We just trying to get an idea of what's going on. So we're going to see this ellipse down here in the XY plane. And then we're going to go up and down to 1/2, -1/2 in the z direction as well. It looks a little funny because that distance in the z direction is so small. Also, I haven't been adding anything that goes that way either. That might help a little bit. Not a lot, but a little bit. Okay, so hopefully you guys get the idea. Okay. When in doubt, just draw an arrow. So that's supposed to be W equals -2. So we've got these ellipsoids. It looks like as W goes out to -infinity, these ellipsoids are going to be really far away from the origin. And they're always going to have this basic like proportion. It looks like the x values, we're always going to go out plus and minus, like let's say a units in the x direction, half of that in the y direction, and 1/4 of that in the z direction all the time, all the way out to -infinity. As we go from -infinity to 0, those ellipsoids are getting smaller and smaller and smaller, but they all have the same dimension. It's just that they're just sort of shrinking. They all have the same proportions. They're just shrinking. And then when W equals 0, we have a point at the origin, and then we're done. No more W's. So it said, describe the changes in the level surfaces of the function as W increases. And we'll just say, I'm going to say large -W. I know that I'm talking about the magnitude though. Let's see, for magnitude of W, absolute value of W, large and negative, we have ellipsoids centered at the origin. let's say as w increases, so we're going from negative infinity back to 0, the ellipsoids, let's say shrink, they get smaller. Eventually reducing to a point. Single point, 0, 0, 0, when w equals 0. There are a lot of correct answers to this question. That's just my way of saying it. You can say it a different way, as long as your explanation is correct and consistent with what's actually going on, then you're good to go. Okay. Last question. And visualizing functions of several variables, we've got this function, f of xy equals 2xy over the square root of x squared or x cubed minus y plus 1. We're asked to sketch the domain of the function. Well, we're looking for the same issues with domain. We don't want to divide by 0. We don't want to take even roots of negative numbers. We don't want to take logarithms of negative numbers or 0. I see division. I see an even root. So the domain of f is going to be the set of all x, y in R2, such that this expression under the radical is positive, so that when I take the square root of it, I get a real number back. And it's also not 0 because I don't want to divide by 0. I don't want 2xy divided by into 0 pieces, which doesn't make any sense. So x cubed minus y plus 1 has to be strictly greater than 0. Now that's an inequality that I can sketch. That's a region in the xy plane. In order to sketch that, I want to take this inequality and solve for y. I'm just trying to get y by itself on one side of an inequality. Yes, you could easily just add y to the other side there. Excuse me. So y is less than x cubed plus 1. And I think I'd like to put y first, so it just makes that more explicit. Instead of saying x cubed plus 1 is greater than y, let's say y is less than x cubed plus 1. Okay. So my boundary for my region is y equals x cubed plus 1. So it looks something like that. When x equals 2, we're going to have 2 cubed plus 1. That's 8 plus 1 is 9. So that's 4, 8, 9. And then when x equals negative 2, we're going to have negative 8 plus 1 is negative 7. Oops, I think I drew that on the wrong line. It should be over here, negative 7. And that should actually go through there. Okay, that's why I need white out, guys. That's okay. We all make mistakes. Whenever I tell you guys that, I always feel like Bob Ross. It's like happy little curve, happy little tree. Okay. All right. So that is the boundary, but I want y to be less than that. So y is going to be less than that over here. Now, when you say y is equal to that, that would be on the curve. Y is less than that is going to be on one side of the curve. Y is greater than that is going to be on the other side of the curve. I'm pretty sure less than is over here. But just to check, like, you can plug in an xy pair that does not lie on this curve and see if it satisfies the inequality. If it doesn't satisfy the inequality, you shade the other side. If it satisfies the inequality, you shade the side where the xy pair is. So I'll pick a really obvious point. This point is not on the curve. It's x equals 4, y equals 0. So we're just going to test x, y equals 4, 0, and see what we get. So you just substitute 0 for y, you substitute 4 for x, and you look at that inequality. It's a true-false statement. Is this true or not? Is 0 less than 4 cubed plus 1? It is. It's true. So that means you're going to shade the side containing that point. I know this is not a calculus 3 concept. It's more of it's more of an algebra concept. But it's helping us to visualize this function. If you're saying, where's that function? Well, this is the domain. So these are all of the xy pairs that I can substitute into this function. Now, if this is the x-axis and this is the y-axis, the z-axis is pointing straight up at us like this. And there are going to be z values associated with every xy over here. I plug in x equals 4, y equals 0 here, I'm going to get a z value. That's going to be the height above that xy plane, or if z is negative, it's going to be the height below the xy plane. But we've done some algebra, sketch that, and it helps us visualize what's happening there. Now the last question in this quiz says, when is the function continuous? Explain your reasoning. Well, it's a function given by this equation. All the functions that you've studied are continuous on their domains. So that's all I'll say. Say f is continuous on its domain as it's given by a single equation. Yeah, there are no sort of complicated functions that have discontinuities in the set of functions that you have studied so far. Let's see, how can I explain this? F is continuous on domain, its domain. Let's say it is the quotient of two continuous functions. And of course, it's well defined when that denominator is non-zero and when that denominator is a real number, which was already taken care of with its domain. So that's it. That is visualizing functions of several variables. If you decide to retake a quiz over F12, it's not going to be exactly the same, but the same types of concepts are going to be on it. So I'll be asking you about domain and range. I'll be asking you to sketch level curves and level surfaces. And we'll be thinking about how those surfaces or curves change as the value of the dependent variable changes.